Okay, so we are going to mainly study about petroleum. So petroleum basically consists of, yeah, first of all, this video is just for revision purpose. So I'm assuming that you know most of the stuff just for revision, and I'm going to explain everything. So petroleum, first of all, uh, it consists of mainly two elements. Number one, crude oil. Number two, natural gas. So we want to see both of them in terms of their properties and their compositions and everything. So first of all, natural gas. So natural gas consists of hydrocarbons with carbon of maximum of 6 carbons, hydrocarbons with maximum of 6 carbons, inert gas, carbon dioxide, H2S, and hydrogen. Okay, so hydrocarbons, these are mostly these are always alkanes, so with carbon less than 6, less than or equal to 6. So that consists of, say, that comprises mostly, uh, you can say, methane, uh, then methane to hexane basically. So that is that. After that, there is inert gases like helium, argon, neon, etc. After that, there is carbon dioxide. Then there is H2S. H2S is a composition that actually uh, controls a lot of functions, because sulfur makes the substance acidic. So that is one condition over there. So if there is, say, sulfur in oil or gas, so we have two terms: sweet oil and sour oil. So if there is less carbon, so if there is sulfide in the gas or oil, so we say that is sour oil. And if there is no sulfide or low sulfide, so that is sweet oil. So we, while we are drilling, we always prefer to drill sweet oil, because the sulfur content tends to damage the equipment we have. So that's about natural gas. After that, we have a term that is known as gas hydrates or clathrates. So gas hydrates are something, these are gas molecules, natural gas molecules that are trapped in frozen water. So as we know, frozen water has a cage-like structure. So within those cage-like structures, gas molecules are trapped, and they form a huge reserve of natural gas. Unfortunately, we cannot exploit those resources, because as we try to extract the gas, the ice melts and the gas escapes. So we do not have sufficient technology right now to extract gas hydrates. Gas hydrates, they are mainly found in, you can say, in Alaska and Siberian areas, the Arctic areas. So that's about gas hydrates. Next, there is crude oil. So crude oil is basically the oil that we find directly from the subsurface or the surface where we're mining. So crude oil is yellowish in color, and it consists of hydrocarbons heavier than heavy hydrocarbons. That is hydrocarbons with the carbon more than 6 hydrocarbons with more than 6 carbons. So that is about crude oil. It is about, it is, we get it in yellow to black color. That's crude oil. Now the density of crude oil, unlike other density of other materials, crude oil density is measured in API units. So there is degree API. So API formula is 141.5 divided by the specific gravity of that oil at 60 degree Fahrenheit, the whole minus 131.5. So you want to basically mug up the formula. The point to be noted out here is that the API value of any oil is inversely proportional to the specific gravity of that oil. So basically, if there is a heavy oil, the heavy oil is supposed to have a low API, while if there's a light oil should have a higher API. In that context, heavy oils have, we classify oil as heavy and light on the basis that heavy oils have API less than 10 degrees, while light oils have API greater than 40 degrees. Yeah, so that is about API. So API is always inversely proportional to specific gravity. That we should also keep in mind while working with APIs. Now the composition of crude oil. So composition of crude oil has distinctly three components. That is paraffins, naphthenes, and aromatics. So paraffins are basically straight or branched alkanes of greater than six carbons. They're alkanes, so obviously every bond is a single bond, and so these are completely saturated hydrocarbons, and they are open chained. So they are like a linear structure or iso structures. The next is naphthenes. So these are cyclic compounds, cyclic alkanes. Again, alkanes, since they're alkanes, they all have single bonds and they have a ring-like structure, that is a closed structure or derivatives of these closed structures. So these are naphthenes. They're cyclic in nature, but all bonds are again single bonds. They're saturated. Uh, After that, the third component is aromatics. So aromatics consists of benzenes or derivatives of benzenes. They are unsaturated and they have resonating structures. So they have alternating uh, double bonds and single bonds. So this structure is basically the benzene structure which we tend to show like this, and these are the derivatives of benzenes. So that is toluene and phenol, and there are other uh, derivatives also. So basically these things they sorry, there's one mistake out here. We show the structure this way. This is the structure of benzene. So benzenes and derivatives of benzenes. So there are other derivatives also, but these are the common derivatives. So this is again the composition of crude oil. So once we have crude oil, so we need to classify that crude oil as per our needs. So the classification, so basically the people who are working are mainly either chemical engineers who are handling uh, the crude oil on site and in the refinery, while there are geologists who are mostly working in the exploration sites, drilling sites. So both of them have their own classifications as per their needs. So the first classification, the engineer's classification, is given by is a plot that has been developed between the percentage of molecular types in this axis and the boiling point of the hydrocarbons. So on this basis, we have a diagram like this, where there is normal paraffins, then there is isoparaffins, then there's naphthenes, then aromatics, then there's naphthoaromatics, and then there are compounds of sulfur, nitrogen, and oxygens. Okay, this is basically the engineer's classification. After that, when we move to the geological classification, there is Mesozoic and Cenozoic oils at depth less than 600 meters. Then there is Mesozoic and Cenozoic oils at depth greater than 3000 meters. Paleozoic oils at depth 600 meters and Paleozoic oils at depth greater than 3000 meters. Okay. Now this is basically an arbitrary classification that has been given with arbitrary depths. So sorry, this is an empirical classification that has been given based on arbitrary depths. So that's the geological classification. To give a more understandable classification, we have the ternary plot. So on the ternary plot, we have the aromatics, we have the paraffins, we have the naphthenes, and this is a diagram that has been given. Okay, so this section is the aromatic intermediates. On top we have the aromatic asphaltic oils, then there's aromatic naphthenic oils. The center is paraffinic naphthenic oils. Lower right is naphthenic oils, and left bottom is paraffinic oils. So this is another classification that is commonly used to classify the oils, and that's it. And after that, we move on to the formation of uh, petroleum. So basically, petroleum was found was like basically formed, like we have a formation of petroleum and everything, and we have been using petroleum for quite a long time. And the first thing that struck people was when we are finding this resource, what is actually the process of formation of this resource, whether we can synthesize that artificially or not. So based on that, we need to build theories about formation of petroleum based on few facts, and we need to explain those facts. So those facts are basically, number one, we are always finding petroleum in sedimentary rocks. Okay, that is important. After that, we are finding petroleum in sedimentary rocks that are present between, we have like confining layers above and below that layer. So there is an impervious layer below the reservoir rock where we are finding, and there is uh, petroleum. We are finding petroleum in places like where there's a impervious layer above the reservoir rock too, and in the laterally they are confined to. So we are finding petroleum. We can extract petroleum from reservoir rocks in these settings. So we need to explain everything. We are also finding petroleum in igneous and metamorphic rocks also in traces, but we are not really bothered about them. But because they are found in very rare and in trace amounts. Okay. So basically, there were two theories of formation of petroleum. So the theories are somewhat like this. So we have the abiogenic and biogenic theories. Okay, so the abiogenic process, there are mainly three theories we have that explain how petroleum is forming biogenically. So the first thing here is the petroleum is of extraterrestrial origin. So we are finding hydrocarbons in meteors and other extraterrestrial objects. So this had a theory that the petroleum that we are finding, they are formed somewhere outside the planet, and it is not formed within the planet. So there was this person named Frederick Hoyle. So Frederick Hoyle gave this theory that if we are finding petroleum in bodies from which Earth itself has formed, so definitely there is a large reserve of petroleum outside the Earth, and probably there is a huge amount of petroleum that is trapped at the core of the Earth. But obviously, we know that sounds rubbish. There were wells drilled as deep as say 5,000 meters, and still we could not find any such reserve. So that was a theory that was given of extraterrestrial origin. The second theory that was given that came up during the World War II period. So basically, what had happened, the German scientists, they had figured out a method to synthesize hydrocarbons. So they passed carbon dioxide at very high temperature, at very high temperature above iron, magnetite and hematite as catalysts, and they could synthesize liquid petroleum hydrocarbons and natural gas, methane, etc. So that became a theory that this might have been the process. Fischer-Tropsch, the name of the process. The third was a mantle-derived theory, that the petroleum we are getting, they are derived from the mantle. So these are the abiogenic theories. The biogenic theory is basically, again, the thing that we all know is that it is forming from decaying organic matter that we are finding on the surface. So this thing is getting deposited, and this is again getting decayed, preserved, converted into kerogen, and this thing is forming. And from kerogen we are getting the petroleum. So that was the theory, the biogenic theory basically. After that, uh, we need to know how this is actually forming, mm, the processes that are involved. Okay, so there are basically three processes that are involved. So first is diagenesis, then there is catagenesis, and then there is metagenesis. Okay, so during diagenesis, the kerogen is actually forming from the decaying matter. During catagenesis, the kerogen that has been formed is maturing, and during metagenesis, it is the last phase where the last of the hydrocarbons they are getting released, and this the last after the release of the last of the hydrocarbons, what we are left with is carbon or graphite. So that is basically the process. Now it is important to have the organic matter that is uh, being deposited getting preserved in the sediments first of all. So basically there are two major prerequisites for the formation of petroleum, that there should be enough organic matter getting deposited in the sediments, and these organic matter that is getting deposited has to be buried uh, very fast under a reducing environment. So basically, uh, four kinds of settings have been identified under which this can form. So the first setting is somewhat like this. Okay, so this is basically a lake. So a lake is getting filled with water. The top part is getting heated. Okay, so it has a lower density, it goes up. Most of the aquatic life is in this upper part, while the lower part has a cooler temperature and is obviously below. So the lower part is devoid of oxygen and has a reducing environment. This thermally induced stratification creates a reducing environment in the lower part while an oxidizing environment in the upper part. So this is basically a lake setting. Okay, the second setting we have is what we call a barred basin. Okay, okay, so this is basically a barred basin. Okay, what happens? This is basically lagoonal setting. The water enters into this part, floods this particular lagoon, and the water leaves in a low tide. This water out here is left behind in the lagoon, so this water evaporates and the salinity of this water increases. In the next high tide, the water again comes and floods the region. So this water that comes has a lower salinity, hence it is less dense and it stays on the top, while the heavier, denser, high water with high salinity that stays in the bottom. With time, this thing becomes anoxic and a reducing environment is devoid of oxygen, and anything preserved or anything organic matter that reaches this point gets preserved. Okay, so this is basically a barred basin. This is a barred basin, this is a lake. Done. Yeah, it should be noted that in this case the stratification is due to temperature. So this is the thermal stratification. Here the stratification is due to salinity. So there's a saline stratification. Third setting is a classic setting of a continental reef. So we have this setting. Okay. So typically what happens in the western coast of the continents, the continental reefs, they have a very high uh, productivity that way. Okay, so in this case what happens, the oxygen content rapidly falls from at a depth between 200 to 1500 meters. So basically if we see the oxygen variability with the depth in these settings, so they are somewhat like this. Okay, this is depth, this is auto content. Okay, so this zone 200 to 1500 meters, this is a zone that is devoid of oxygen. Okay, so in these settings what happens, this forms a reducing environment. Okay, so this area is also, we can say that, continental shelf. Continental shelf. Okay, now the fourth case, uh, it is again a theoretical case, but we do not have any uh, example right now in today's world. Okay, so this is basically ocean basin that is anoxic. Okay, so say we have, this is an ocean basin. So this part, the ocean floor is anoxic. Okay, so these are the four classic cases where there can be anoxic environments under which the organic matter that is getting deposited is preserved. Okay, now after that we talk about the formation of kerogen. Once this thing, uh, the organic matter is getting preserved, we move back to this process, diagenesis. So what happens during diagenesis? The organic matter that is there, organic matter decays, okay, gives out methane, okay, gives out methane, and then the oxygen to carbon ratio, this thing falls, while the hydrogen to carbon ratio is constant. Okay, so during diagenesis, organic matter decays, kerogen forms, it releases biogenic methane, the oxygen to carbon ratio falls. Oh, sorry, it's methane and carbon dioxide. Oxygen to carbon ratio falls, the hydrogen to carbon ratio that remains constant. The next process is catagenesis. So during catagenesis, what happens? The kerogen that has formed, it, okay, this is depth, okay, depth increases, temperature increases, pressure increases along these, okay. So in during catagenesis, this kerogen matures, okay, kerogen matures, release petroleum, okay. During this time, the hydrogen to carbon ratio that starts falling, while this ratio remains constant. Okay, now there is a sequence of release of petroleum. So in the initial phases, the heavier hydrocarbons they are released. So initially there is release of oil. In the later phase, there is release of gas. Okay. In the last case, release of last hydrocarbons. Okay. What is left is right now graphite. Okay, during metagenesis there is the release of last hydrocarbons and graphite is left out there. Okay, so these are the basic processes, overall processes, what I can say. Now I'll explain you the entire process in detail. Now this kerogen that is forming out here in diagenesis, the composition of kerogen largely depends on the composition of the organic matter that is getting deposited in the very first place. So we have basically three types of kerogens. So, about talking about the organic matter, so we have first of all few organic matters. We have few things. Number one, there is carbs, then there is lipid or fat, there is proteins, and there is lignin. Okay, so carbs are basically you can say the thing uh, the basic thing is a glucose molecule, that is H12O6, and this thing polymerizes and forms cellulose, starch, and a lot of other things. So that is basically carbs, carbohydrates. Then there is lipid, which are you can say polymerases. So polymers again, they have oils. So lipids are basically unsaturated ones, oils. After that, there is proteins that has nitrogen in them, so they form amino acids. The amino acids, they polymerize with each other and forms long chains that are known as proteins. And then there are lignins. Lignins, they are mostly found in higher plants. Proteins, they are found in animals mainly. Carbs and lipids, they are found in both. Okay, so based on that, we have basically few types of okay. So okay, this is type. Okay, first of all, this, just a minute. This is H is to C ratio. This is O is to C ratio. So this is basically the kerogen maturation pathways for different kinds of kerogens. So this is type 1 of kerogen. This is type 2 of kerogen. This is type 3 of kerogen. Okay, type 1 is basically sapropylic. Okay, after that, okay, uh, this is type 2 is lipid, and then there is type 3 is basically humic. Humic kerogens. Okay, so sapropylic kerogens, they are of algal origin. Okay, lipid rich are from planktons. Humic is from land plants. So they have a high content of um, humic kerogens. They have a very high content of lignin. So under certain circumstances, this lignin thing undergoes diagenesis to form coal. Okay, so that for that it has to be buried as peat. Okay, so basically these are the three types of kerogens. So once the maturation starts, the HC ratio, initially the OC ratio falls, after that the HC ratio falls, and finally we reach this point. It is basically graphite. Okay, then we have this phase, three distinct phases we have. Okay, so the dotted phase is basically gas, the stripe phase is basically oil. So initially there is diagenesis, the white part. After that it reaches the oil window, during which oil is released from either of the from all of the kerogens. After that they reach a part where gas is released, the later part of catagenesis, and finally this is a metagenetic phase. So, so if we see it like this is dia, this is cata, this is metagenesis. Okay. Further, if we divide, this is oil window, this is gas window. Okay, so this is basically the maturation pathways of kerogens. So if we plot the same thing with a thermal gradient and depth, so we get something like this. This is depth, this is thermal gradient. Okay, so what happens, this is biogenic gas, this is thermal gas. So as we see that gas is released in two phases. So initially during the diagenetic phase, a part of the gas is released. After that there is formation of oil, and after that we have the release of the thermal gas. During this part there is release of oil. Okay, in another way we can use another diagram that is explained. So okay, this is again depth. So this is biogenic methane, this is dry gas, then there is oil, that is this part. Okay, so this part is basically known as oil window. This is gas window. Okay, after that there is graphite, right? Okay, now we have certain to estimate the age of the petroleum and the maturation of the petroleum. We have certain paleothermometers to check the temperature to which this particular oil has been subjected to. So for that we can either check the oil that has been subjected to, or the source rock that has been subjected to a particular temperature. For that we have certain paleothermometers that can be chemical paleothermometers or biological paleothermometers. So the chemical paleothermometers are, first thing is carbon ratio. So we need to check the carbon ratio of the hydrocarbons, the HC ratio and the OC ratio, so we get to know the thing, can the thermometer, the temperature to which the oil has been subjected to. Next thing is electron spin resonance. So that electron spin resonance is basically it, what to say, this ESR, the crude oil, it has certain free electrons, and the nature of these free electrons, they are kind of controlled by the temperature to which it has been subjected to. Based on those nature that is reflected by the ESR or the electron spin resonance, we can find out the the temperature to which it has been subjected to, and hence the maturity. Third is pyrolysis. So when we get the source rock, the hydrocarbons in that, so they are heated to a very high temperature, and this the hydrocarbons that are there, they crack and they form shorter hydrocarbons. The complex hydrocarbons, they form simpler hydrocarbons, and based on that it is subject the maturation of the source rock is checked. Fourth is gas chromatography. So basically it's like most of the chromatographs, but I do not have much idea about this process, so can't really say. After that there is uh, clay study. So first of all, clays reflect a lot. They convey a lot of information about the diagenetic changes. So diagenetic changes in the clay, they are studied. Recrystallization of clays, they are studied, and based on that, the maturation of the source rock as well as the oil is calculated. Then there is fluid inclusions. Again, they involve the study and then study of diagenetic changes. The biological ones are, number one, pollen color. So basically what happens, pollens are made up of a very complex and resistant substance known as sporopollenin. So this pollens, when they're subjected to higher temperatures, they tend to change their color from light yellow to orange to brown. Like there's a series of colors they change according to temperature. So pollens are extracted from the oils or the source rock, and the colors of the pollens they are analyzed under a microscope, and we can take the temperature from to which it has been subjected to earlier. A similar thing is done using vitrinite. So we check the reflectance of vitrinites. So vitrine is basically a coal maceral. So you might have studied in coal petrology also that this vitrine is one of those four macerals that coal has. So even in coal petrology, we study the maturation of coal using the reflectance of vitrines. So vitrines are also found in oil. So the vitrines from the oils they are extracted using acid treatment, and the reflectance is uh, and they are mounted on a slide, and the reflectance is checked. So based on that, the maturation of the oil is calculated. So this is about the formation of the kerosene and maturation of kerosene.